Welcome to a brand new deep dive. I am really excited about today's topic because we have a fascinating stack of sources to go through.
Yeah, it's a pretty provocative batch material today.
It really is. I mean, we're looking at this April 2026 blog post by Elias Muzman. It's titled, "A System Cannot Prove a Property of Itself." Plus, we've got all these internal strategic foresight documents, some voice audit tool notes, and a bunch of architectural analyses on AI governance.
Right. Which sounds incredibly technical, but the core issue is something that affects literally everyone.
Exactly. Our mission for this deep dive is to uncover why the way we currently verify and trust AI systems is structurally doomed, like mathematically doomed to fail, and how a radical return to the physical laws of computation might actually be the only way to save it.
It is a complete paradigm shift.
Yeah. So whether you are a C-suite executive who signs off on AI deployments, an engineer, or just someone listening who is curious about the future of tech, you really need to hear this. The way you think about AI hallucinations and safety is about to completely change.
And honestly, I think the best place to start is to look at the exact moment where the failure begins today.
You mean the boardroom sign-off?
Exactly.
Yeah.
Because that's where the illusion of safety gets formalized.
Okay, let's set the scene for the listener. Imagine you are a chief information officer, right? Or maybe a general counsel. You are sitting at a big conference table, and you are about to sign off on a massive enterprise AI deployment.
A system that's going to handle sensitive data, customer interactions, the
Yeah.
works.
And you look at your engineers and you ask, is this thing safe? Can we guarantee it won't go off the rails?
Yeah.
And the engineers say something that sounds incredibly reassuring. They say, don't worry, our inference is deterministic, so the halting problem doesn't apply.
And if you're an executive, you hear credentialed engineers use words like deterministic, and you sign the paper.
Right.
You assume you've just been handed a clean bill of health.
Right.
But you've actually just stepped right into a massive fiduciary trap.
Okay, let's unpack this. Because, I mean, I would probably sign that paper too. It sounds totally logical.
It does.
If a system is deterministic, meaning if I put in 2 plus 2, I get 4 every single time, doesn't that mean we can predict its behavior and verify that it's safe?
Well, it sounds reasonable, but it completely fails a structural test of computer science. And to see why, we have to go all the way back to 1936.
Back to Alan Turing.
Exactly. Alan Turing, along with Kurt Gödel in 1931 and Henry Rice in 1953. Turing mathematically proved that no general computing machine can look at an arbitrary program and decide whether it will eventually halt or just run forever.
Right, the halting problem.
Yes. And he proved it using this mathematical concept called diagonalization.
Okay, diagonalization. I mean, I've heard the term, but you're going to have to translate that out of the 1930s math papers for me.
Yeah, let's simplify it. Imagine you build a perfect prediction machine, like a piece of software that can analyze any other software and tell you exactly what it's going to do.
Sounds like the ultimate governance tool.
Right? But Turing realized you could just take that predictor's output and feed it into a new program that is designed to do the exact opposite.
Oh, I see where this is going.
So if your perfect predictor says, this program will stop, the new program takes that answer and intentionally loops forever. If the predictor says it will loop forever, the new program immediately stops.
So it's basically like dealing with a stubbornly contrarian child.
Pretty much, yeah.
If you predict the child is going to sit down, they hear the prediction, and they just purposefully stand up just to break your rule. The system breaks because it's aware of its own prediction.
That is a highly accurate way to look at it, actually. The paradox is created by self-reference, and that is the crucial thing those engineers in the boardroom are missing.
Because they think the halting problem is about randomness or glitches.
Exactly. They think it's about stochastic failure, but it's not. It is fundamentally about self-reference. Any Turing-complete system, which is basically any modern software, contains descriptions of itself. So when it tries to decide a definitive property about its own behavior, it has to reference its own description. And that loop is where decidability collapses. A computer simply cannot look at itself and reliably tell you if it's behaving correctly.
But wait, I'm still stuck on the determinism argument. Let me play devil's advocate for a second.
Go for it.
If I pin all the inputs, right?
Sure.
I don't change a single weight in the neural network, and I run the exact same prompt through it. I get the exact same output. The math is fixed. So why doesn't that predictability equal safety?
Because you are confusing a mathematical property with real-world behavior. Yes, the math is fixed. Determinism is a property of the transition function. But in the real world of deployed AI, your inputs are never actually pinned.
Well, yeah, because users are constantly asking weird, unpredictable things.
It's not just users. Context windows grow as a conversation goes on. Malicious actors use prompt injections. The AI uses external tools that feed new data back in.
Oh, right. And fine-tuning physically updates the weights.
Exactly, the baseline drifts. So running deterministic inference on drifted inputs doesn't verify safety at all. It just gives you a deterministically wrong output twice.
Wow.
You're just faithfully reproducing a corrupted state.
Okay, so if software determinism is a dead end for verifying safety, why is the entire tech industry currently spending billions of dollars building, cryptographic hashes and software dashboards to prove their AI is safe? What are they actually proving?
What's fascinating here is that they're proving identity, but they are marketing it as role continuity.
Identity versus role continuity. Okay, break that down for us.
Industry standard verifications like cryptographic hashes, signed model cards, trusted execution environments, they only prove identity. They answer a very basic question. What are the bits?
So it's like a digital tamper evidence seal.
Exactly.
It reminds me of hiring a security guard. A fingerprint scan at the door proves the guard is who they say they are. That's identity. But that scan tells you absolutely nothing about whether the guard is actually watching the security cameras or just sleeping on the desk in the back room.
That is the perfect analogy. Watching the cameras is role continuity. You need to know if the system is still performing the functional role it was authorized to perform.
Right.
Because if the role has drifted, if the guard is sleeping, the system is not trustworthy, even if the cryptographic signature on their ID badge is flawless.
But wait, aren't things like policy engines designed to watch the behavior? They sit on top of the AI and monitor what it does. How do they fail at role continuity?
Because of the exact structural failure Turing warned us about. It's software checking software. Dashboards, policy engines, governance tools, they all run on Turing-complete substrates.
Oh, I see.
They are capable of executing arbitrary programs, which means they share the exact same failure modes as the AI they are supposed to be watching.
So they inherit that infinite regress of self-reference. If the AI can hallucinate, the dashboard checking it can also hallucinate or be tricked.
Precisely. You cannot use a system to reliably verify another system if they belong to the exact same computational class.
Okay, so if Turing-complete software cannot check Turing-complete software without falling into a paradox, what do?
Yeah.
We have to look completely outside the realm of software.
Yes. We have to look at physics. We have to drop down to a lower computational class.
Meaning hardware.
Specifically, hardware-level combinational logic. These are physical gates that have no program counters, no loops, no internal memory states.
So they fundamentally lack the ability to hallucinate.
Exactly. Electricity just flows in and out based on a fixed physical pathway. It executes a single hardware cycle, like a bitwise XR operation, to verify an action.
This reminds me of the mailbox analogy from the sources. I love this part.
Yeah, it's a great way to visualize it.
It says, if you have a physical mailbox and it's full of mail, you literally cannot put a second package into that exact same space without physically removing the first one.
Right, the classical exclusion axiom.
Yeah. Two physical configurations cannot occupy the same location simultaneously. Displacement is a physical witnessable event. It's undeniable.
And that physical boundary isn't just a new trick. It actually echoes one of the most important architectural shifts in human history. Luca Pacioli's invention of double-entry bookkeeping in 1494.
Okay, wait. 15th century accounting? How does that connect to AI hardware?
Well, before Pacioli, merchants used single-entry accounting. It was basically just one person writing a narrative in a book. If they wanted to lie, they just wrote a different number.
No systemic check.
Right. Pacioli's genius was requiring two structurally independent records, credits, and debits that had to perfectly reconcile. In paper bookkeeping, that independence came from two separate human parties with opposing incentives.
But with AI, software is just one big single-entry narrative. It's all the same party.
Exactly. So to get that true Pacioli-style independence in silicon, we need two separate computational classes. You have the Turing-complete software proposing an action writing the narrative, and you have the hardware gates verifying it.
And the hardware can't be fooled by software attacks.
Right. The physical ledger reconciles the software ledger.
This gets into some really deep theory in the sources, too, about the physics of trust. They talk about systems being autocoincident versus detached record.
Yes, that physics theorem is the core of all this. Physical systems are autocoincident. That means their current state and the history of how they got there are the exact same thing.
Like a footprint in the mud, right? The shape of the mud is the literal history of the foot stepping on it.
Exactly. It's governed by Landauer's principle of thermodynamics. You cannot erase physical information without expending energy and leaving a heat signature.
But information systems like AI software, they don't work like that. They are detached record systems.
Right. In software, the event and the record of the event are completely divorced. A bit at a memory address doesn't inherently encode how it got there. You don't know if the authorized program wrote it or if a hacker overwrote it later.
State and history are easily separated, which means the record is incredibly easy to forge.
So by using hardware gates, we are taking that detached, floaty software and anchoring it to auto-coincident physical reality.
Which finally breaks that loop of self-reference.
It anchors the intention to the substrate.
Okay, so what does this actually mean for the AI itself? If we put this physical anchor on it, is this just a heavy safety brake that slows the whole thing down? Or does it change how the AI actually drives?
Oh, it changes how it drives entirely. It creates what the sources call a capability phase change.
Wait, really? A safety check makes it more capable?
Yes, because you are removing an architectural bottleneck. Right now, conventional AI performs its search step finding information and its inference step reasoning about it in the exact same representational space.
So it's trying to remember a fact and think about a fact using the same blurry parameters.
And that's why they hallucinate. They lose track of the boundary between reading and thinking. The sources call this the hallucination floor.
And to fix that, AI companies are spending millions on compute power just to double-check the model's own work.
Right, the denoising tax. But if you decouple search from inference at the hardware level using that physical anchor, you remove the hallucination floor.
And the denoising tax goes away.
Exactly. Safety and capability are actually the exact same property viewed from two different angles.
So substrate-anchored intention allows the AI to actually sustain agency over long time horizons. It doesn't get confused and drift off topic.
Yes, it can actually be trusted to act autonomously.
I want to make sure you, the listener, understand why this is such an urgent reality. This isn't just theory. The sources point straight to the EU AI Act, specifically Article 14.
Which is coming up fast.
Yeah, August 2, 2026. This law legally requires deployers of high-risk AI to correctly interpret outputs and detect anomalies. And based on what we've just discussed...
Detecting anomalies purely in software is mathematically impossible.
Right. And the insurance industry already knows this. If you go to a company like Munich Re right now and try to buy AI liability insurance for role continuity, the cost is literally $0 globally.
Because they won't underwrite it. They only underwrite physical signals, not software narratives.
So ignorance is no longer a defense for executives.
Not at all. Now that this architectural truth is public, it's out there in patent 1,637,714. It's in Moosman's blog. Executives who deploy purely software-based AI are carrying unmeasured liability personally.
You can't just hide behind a software dashboard anymore.
No, because you have been warned that the dashboard itself is subject to the halting problem.
Man, what a journey today. We started with this illusion of deterministic software in the boardroom, discovered the trap of self-reference, and realized that true AI verification requires different physics, same silicon. We have to anchor information to hardware.
It's the only way to prove a system is doing what it says it's doing.
But before we go, I want to leave you with one final, lingering thought to mull over on your own. We've established that pure information, this detached record digital space, is incredibly fragile. It's easily forged.
Right.
We need physical hardware just to prove an AI isn't lying to us. So what happens to human society as we relentlessly digitize our own memory, our laws, our history, our personal identities? We're moving all of it entirely into that detached record digital space.
That is a chilling thought.
Will we eventually reach a point where we need physical hardware-level anchors just to prove to ourselves that our own human history hasn't quietly drifted? Are we going to need auto-coincident reality just to know who we are?
That is the ultimate question of the digital age.
It really is. Well, thank you for joining us on this deep dive into the source material. We hope this changed how you look at the systems running our world. Keep questioning the digital landscape around you, and we'll see you next time.